felt like update time. So I thought I'd spend a few minutes and walk through some of the thermostat project. And yeah, here it is. Here's pretty much all the major pieces. The first two pieces you saw in the original video, which was the Raspberry Pi W and the OLED bonnet from Adafruit with all the buttons. And this, which I made, which was just a simple little board because I had a bunch of LEDs. I think I described that in that first video. But the two new pieces are the BME680 and the relay board, right there. And they're all wired up, and actually it's now controlling my air conditioning. So we have, well, actually air conditioning and heating through a 4-wire system. The wires are all the same color because it is exposed in my home, and so I wanted to make it look a little neater, look a little nicer. So there's just these 4 wires that run up to the thermostat on the wall right now, and until this gets condensed into an enclosure that I will likely be 3D printing. So we'll start with the BME680, which is from Adafruit. What that Bosch sensor has on it is temperature, humidity, barometric pressure, and a representation of air quality that comes back as a resistance value. And that's really, really cool. There was some example code that I found from Adafruit. There's also some example code from the company that I end up using the library from, which I believe is called Pimironi. We're going to go with that, Pimironi. I'll put that also in the notes, the library that I used, and the link to this part on Adafruit. Now, the reason I use the Pimironi library is because this, you can use the Adafruit library, but it's part of something called CircuitPython, which seems really cool, and I haven't really had a chance to play with it, but I'm building this out in Python 2.7.16. And the reason why I didn't go straight Python 3 is because, one, I was familiar with Python 2.7, and I wanted to just get this thing working. And there's always time in a project to go back and refactor things when it's not a product, it's just messing around. So just wanted to get this thing to work as opposed to learning the ins and outs of Python 3. So the library that Pimironi has is a 2.7 library. I believe it also is compatible with Python 3, but it is functioning at least with 2.7. There are some peculiarities that I noticed with that library, especially in the way that it considers taking sensor samples and partitioning between taking a temperature, humidity, barometric pressure sample and taking a resistance sample for air quality. And the reason I say that is because I found that if you just look at the sample code that Adafruit includes as part of this product, which is good, it's a very good starting point, is how samples are taken by the BME680 for air quality. And I think this is an important thing to note, which is if you're using this to sample air quality, I have found that if you sample air quality at a temporal rate of any faster than once every 20 minutes, you will affect the temperature and the humidity reading that you are taking. Because every time the sensor goes to make a sample reading of the resistance to represent the air quality, it has to heat up a little hot plate that's on this thing, and then it heats it up, and I'm assuming it heats it up to like measure what the resistance is of the particulate or volatile organic compounds that are sitting on the hot plate, and then it measures its resistance, and I think it actually goes to a higher temperature to kind of burn it all off, and then it returns back to its idle state. I'm not 100% sure on that, but that's kind of how it was described by Adafruit, and I looked through the Bosch data sheet a little bit to kind of understand what was going on with that as far as its flow diagram and state. state machine for the air quality sensor. It doesn't seem that in any of the documentation from Adafruit or even in the Bosch datasheet that there really is any concern about how frequently you should expect to be taking air quality measurements without impacting temperature. And so originally I had it set to only sample the indoor air quality every 5 minutes, and I still noticed that it resulted in the temperature being off by about 1 degree to 1.5 degrees as compared to 2 other temperature sensors and an infrared non-contact thermometer. I know they all have different tolerances, but they all pretty much agreed with each other. So 3 different things agreeing with each other, and then this thing being off by 1.5 degrees seemed to indicate that there was something a little bit funky. And I could prove that out if I decreased the amount of time between samples of indoor air quality. So I took one every 5 seconds and then once every 1 second. Then I would see the temperature rise by 5 degrees, by 6 degrees, 7 degrees, sometimes up to 10 degrees Fahrenheit, because that hot plate was affecting the temperature. And consequently, also, I would see a decrease in the humidity because it was drying out the air just in that area around the sensor, or just inside the sensor itself. So something to bear in mind if you're using the BME680, wanting to use the indoor air quality sensor measurements and are curious about the temporal rate, how quickly you might want to be sampling. I would say a good rule of thumb is about once every 20 minutes. The other thing that I noticed with the BME680, with the sample code that I was looking at, in order to get what is a indoor air quality at 93.48%, and then the score, the raw score, is 32.58. That sample code is out there. It is just to provide you an indoor air quality measurement as a percentage and just a score. And so that works really well, except there are some things that they included, assumptions that were made as far as like what the indoor humidity should be. And for example, they say that in the sample code that the indoor air relative humidity should be between 35% and 42%. Now I live in the Midwest, and that's usually never the case. That's a pretty narrow band, 38 to 42%. And if you go outside that band, then it starts to actually ding you percentage points as far as the quality of your indoor air, because the humidity is either too high or too low. So I'm investigating where that assumption came from, and I might make some changes to reflect that, because in the winter, the humidity is way lower than that, and you may want to adjust the score based off of that. Other than that, the only thing I had to do is make sure I jumpered this so that it used the alternative I2C address. So that's what the Pimironi hardware expected. This is the Elegoo module. I bought it because it was cheap and it would serve all the purposes that I needed it for, as well as having a handy function where you could jumper out by removing this jumper, the relay coils. So it has little LEDs on it that are along the bottom right here. And if I go and just forcibly turn on the air conditioning right now, hang on 1 second, you can see that the LEDs will come on, but the relays will not click. So it's really cool for debugging and knowing the status of various things without actually having the thing connected all the time and worrying about disconnecting and reconnecting and all that other stuff. So that was pretty cool. There it goes. Just turn on the fan and the cooling. This also contains a fourth relay. So I only really needed 3 relays. One was, if you can see the markings on here, there is C, H, FN, and FT. And the C is for call for cooling, H is call for heating, FN is fan, and then the final relay is the fault relay. And so how I have this wired up is 24 volts is right here. This is coming from the furnace controller. It comes into the normally closed contact on the relay. And that normally closed contact is shunted between here and the yellow wire. And then the yellow wire goes between, it's basically a node that goes out to each one of the relays, the 24 volt side that's open. Because all you're really doing whenever you're turning on your thermostat and are running either heating, cooling, or fan is you're shunting 24 volts back to the furnace controller. That's all it does. And so when you shunt back to the 24 volts, it turns on either heating, cooling, or fan. The important thing was this fourth relay, which is the fault relay. So while the wiring coming in is sitting on the normally closed contact of the relay, all the other ones, as you can see, are on the normally open. When the relay is energized, these three relays will close across their normally open contacts and shunt back to the furnace controller. However, the fault relay, if it were to energize, that's this in4, then it would open on the normally closed side of the contact, and it would open all these three channels. So there would be no way for the fan, heat, or for cooling to have any effect, because 24 volts is basically disconnected. So this has proved helpful a couple times. It would be trapped by the fault handler that I had written, and the first thing it would do would just turn on the fault relay. So this relay module is really quite awesome for the cost. I mean, you have great optical isolation. The board's laid out very nicely. Like I said, it's quite cheap. You have pinouts that are already on the board, so you can go ahead and plug things in and play around with it. It seems like it's designed for just nice and easy plug and play. And these terminal blocks are pretty high quality for the price, so they work quite well. Plus you have this awesome jumper that can remove energy transfer to the coils, so you can just do a visual check to make sure that what you expect to have happen is happening the way that you'd like it to. A few strange things that I found with this module. One is that it operates in inverse logic. So to energize the coil, you set everything to logic low. When everything initializes and you're setting everything up and you're initializing GPIO pins, it sets everything to logic low. And so when you set to logic low, all the relays turn on. So when this thing powers up, it initializes the relay, and then immediately after, it sets the relay to logic level 1. So for a very brief period of time, you see the light come on and then it goes off. It's so fast that it doesn't even actually actuate the contacts, because the coil doesn't move that fast to actually make anything happen. The electromotive force inside there, just nothing happens. So it's something to consider with this module. The other thing is that the relay coil current draw, or the overall power draw, is quite high. Now, it's enough for this to be wired right into the Raspberry Pi. There it is, poking up from the bottom. And running it off a standard USB 1.5 amp, 5 volt system, it's perfectly fine. In fact, I'll show a little video when I was doing testing with it. I ran all the relays all at the same time. So all 4 relays came on at the same time, went off, on, off, to draw the inrush current across this cabling, across the Raspberry Pi, and across the USB port that was modestly rated at about 1.5 amps to make sure that it didn't exceed what everything was able to handle. And then I went and stepped through 1 relay, 2nd relay, 3rd relay, 4th relay, turned them off, turned them back on again. Ran that for quite a while and never had anything reset or cut out. But it does draw, I think it's about 1/3 of a watt to 1/2 a watt. So that sums it up for the hardware and the implementation of the hardware and the implementation back into the Raspberry Pi. And maybe we'll walk through one example of it going through power on. You can see the console output, and it should shut off. I don't need to run the air conditioning because it's not very warm in here right now. There we go. And I'd rather not have the relay stutter when I put this jumper back down.